All right, students. So, we'll continue with the discussion that we have been doing on the quantum mechanics part of this course. And it's been well established that um, all the microscopic particles, we have given examples with light only, which means the quantum of light, they are called photons, and we have given examples with photons. But I have told us number of times that photons are of course massless particles, but similar quantum phenomena are shown via, they are exhibited by electrons and neutrons and so on, which are more massive particles which have mass. So since we have been able to talk about the wave particle duality, which means that every particle, every quantum particle has a wave description, and de Broglie fortunately have linked the wavelength of the wave to the momentum of the particle, which was by this relation. We are indeed talking about a wave and its equivalent particle description. The formalism of quantum mechanics proceeds with this wave description of the particle, and we'll see that there is a corresponding equation that talks about the behavior of the particle, or rather the properties of the particle, and we'll call this as a wave function. It's in general a function of x and t, and we'll see that we'll call this a wave function, or even at times we'll call this as an eigenfunction. I'll tell you what this means, and we'll also call it a state function, or simply a state. Okay, and in going through this formalism, which is to establish the properties of the particle through its wave description, which is also called as wave mechanics. In this thing, we'll introduce a new formalism, or rather notation, which are called as a Dirac notation. You can do without Dirac notation, but our description will minimally involve these Dirac notation. But very importantly, we'll talk about linear algebra, and linear algebra is not something that you have done yet, but you'll be doing in some mathematics course. Will only introduce the key elements of this linear algebra. That's what's important to us. Okay. So coming to this function, let me just keep this psi for the moment, and we know that it has a number of names. Okay, so this is in general a complex quantity. Okay, and what does complex quantity mean? Complex quantity means that it has both a real part and an imaginary part. Okay, so by itself, psi does not have a physical meaning. Okay, but it is related to a quantity which we call it as the probability density, which is simply given by the psi star xt multiplied by psi xt. X and t are the position and the time, or the location and the time of the particle. So this is represented as mod square, and that's why we said that it's in general a complex quantity. But you'll also see that we talk about wave functions which are real functions of x and t and so on. But in general it's complex. So this is called as the probability density. So what does it mean? The probability density tells you the probability to find a given quantum particle at x and t. So this reinforces our probabilistic interpretation of quantum mechanics, that you cannot say that the particle would be found at a given space-time point x and t, but at the most what you can say is the probability of finding it at this point is given by this mod psi square. And since if there is a particle, since we should find it somewhere in space between minus infinity to plus infinity, this probability density, when we sum it over all x between minus infinity to plus infinity, we should get equal to 1, right? Because that's the total probability. We know the probability, normalized probability, is always equal to 1, which tells you that this thing is 1 for all t. It's equal to 1, we have said that, for all t. Okay, so which means at any point, if you are looking for an integrated probability, it should be equal to 1, which means that we should be able to find the particle somewhere in space between minus infinity to plus infinity. Okay. So by itself, the wave function does not have a meaning or a sort of physical interpretation, but the interpretation comes from this psi mod square or mod psi square, which is psi star, which is a complex conjugate of psi multiplied by psi itself, and which when integrated over all space should give me 1, which also demands that this psi should be normalized, which we'll see what normalization mean. Okay, now Dirac is a well-known person who has contributed to the development of quantum mechanics a lot in those days, and he has introduced a notation which is really a shorthand notation, and we can go ahead with the notation here. So let's call it as a Dirac's notation. And the notation is really simple. The notation says that such a quantity, or let us even write without, so this quantity is represented by just this inner product written in this particular fashion. Okay, where this is called as a ket and this is called as a bra. Okay, so it's basically it's a bracket which been sort of split into half. So so this psi immediately gives you a feeling that this psi we are talking about is of course a function of x and t, but it should give you the state of the particle, should describe the state of the particle, and that's why this psi is really a column vector. Okay, so which has entries, say for example, so we'll write a column vector like this, where we'll write it as psi 1, psi 2, and so on, and some psi n, and the conjugate of that, or the bra of that, is actually a vector which is like something like this, which is your psi 1, psi 2, and a psi n. Okay, so writing this notation, that is this one, is actually equivalent to writing it. So this is a row vector, and this is the column vector. Okay, So this cross psi get psi actually means that you have a column vector, a row vector which had to be multiplied by a column vector, and when you do that, you get a number. So this is called as an inner product of two vectors, and it is quite important for us to understand that they physically mean something which we are going to come at. Okay. Now, these are preliminaries of linear algebra. I'm sure that you haven't done a course on linear algebra, but what you can do is that you can look up uh, even simpler books like the Shom series books on linear algebra and get a preliminary idea. I'll be providing you the ideas that are mostly needed for us to discuss quantum mechanics. Okay. So let me give you an idea of a term called basis. Okay, and to understand it very simply, if I just simply write down a table, okay, which has rows and column, and there are some numbers put in these boxes here, or some quantities that are put in there, and so on. You'd be wondering what this box or what this table correspond to. Does it correspond to anything physical, and so on? So we need to say that these contain, the marks for say for example 5 students in 3 of the courses that you are doing, say PH101, CH101 and MA101, and there are these 5 students, let's call them as A, B, C, D, E, and these are physics, chemistry and maths. Now it makes perfect sense that student A got so much marks in physics course, chemistry course and the math. Similarly, B, C, etc. You see all their marks and you know exactly that how much or what grade someone has got and so on. So I have actually provided you a basis. Okay, so this is called as this putting this ABCD or this PCM is actually providing you a basis to the problem. Without the basis, it wouldn't make any sense. For example, you have also looked at the uh, coordinate systems such as Cartesian coordinate system. Okay, so Cartesian is one you have looked at. I'm talking about 3D, so let's talk about spherical polar is another one that you have been exposed to. You know what the r theta and phi are, and how the Cartesian coordinate system are related to the spherical polar coordinate system. There's a very important difference that these are the unit vectors are constant in the Cartesian frame, whereas they are not in the spherical polar or in the cylindrical. So they vary in space, and we have been able to actually write down a transformation relation between the unit vectors corresponding to the Cartesian coordinate and the spherical polar or the cylindrical or cylindrical to spherical and so on and so forth. Okay, so these are individual bases that we have used in order to write down a vector. Okay, so that's the basis of the vector, and because a physical quantity remains absolutely insensitive to the basis chosen, so we know that there had been a connection or a relationship between the eigenvectors, or not eigenvectors but the unit vectors in this coordinate system and this coordinate system and this coordinate system and so on and so forth. Okay, and because these relationships exist, and these relationships will see that they are unitary relationships. What it means is that if I define a unitary operator, which we write it as u, and you take a dagger of that, I'll tell you what dagger means, and you multiply with original u, then it gives you 1, and this u is actually a matrix which gives you a transformation between one coordinate system to another coordinate system. So what I mean to say is that your r cap, theta cap and phi cap, they are related to the x cap, y cap and z cap in a way, and this is, sorry, there has to be equality sign. Okay, so this is a matrix that I'm talking about here. This matrix is unitary, and what it means by taking a dagger is that you have to take a transpose of that matrix. So taking transpose means that you convert the rows into columns and also take the complex conjugate. That is, if there is a I, you change it to minus I. If there is a you change it to A star, and so on and so forth. So you do these two operations and then it becomes a dagger. So you take that matrix after taking a transpose and complex conjugation, that is a dagger, and you multiply it by the original matrix. So this is your U matrix, and that gives you unitary, that gives you an identity matrix. Identity matrix is nothing but it can be an infinite dimensional matrix with the diagonal elements being 1 and all the off diagonal elements will be 0. Okay, so that's a relationship between two bases that we have seen, any two, and a similar thing, idea exists in quantum mechanics as well. Okay, let me tell you that now. So we write down the wave function in a certain basis. Okay, and I'm using that Ket notation, Dirac's notation. But as I said that these notations, you don't have to stick to that. While calculating certain quantities, we find it more easy to go back to the definition, which I feel that I have not written that. So this means that this is equal to, so when you integrate over minus this to this, this is your really integral representation and the Dirac representation. So what you represent by an inner product, which is a bra psi and a ket psi, is actually integrating the whole thing over all space and the mod square of that. And this is the really the connection between this so-called, I mean, Dirac has invented it in the 1930s, so it's not really something that's recent, but it's been used quite extensively in the context of quantum physics. So this psi will be able to write it in terms of some alpha n and some ket phi n, and n in principle go from 0 to infinity. Okay, and so what is the connection with what we have been talking about? This is the basis, and we'll call it as a basis function. Okay, and this is the amplitude. Okay, so this is the amplitude for each one of those. So let me give you an example. You have seen this problem of Schrödinger's cat that we have talked about. So the cat is inside that glass box, and we have left it with a poison capsule and things like that. And it depends on the cat whether to do a mischief with that, break that poison and get killed, or if it doesn't do that, it is alive. So each one of the phi n's, we can call it as, so there are two phi n's in that problem. One is alive, let's write it as a ket, and also a dead. Okay, so these are the two possible states of the system. and that formed the basis. So as you have not seen the cat or not entered the room to see what's the state of the cat after a while has passed, then in your mind it's this alpha n's would be 1 by root 2. Why it's 1 by root 2? Because the whole thing, the state of the cat, so let's call it a psi cat, is written as 1 by root 2, the cat being alive, plus a 1 by root 2, the cat being dead. And you make a measurement, it collapses into one of the states, alive or dead. Okay? But before you have made that measurement, the state of the cat, which is here state of a quantum particle, is in the superposition of states, okay, which forms the basis of this problem. So in this particular case, the basis is formed by these two states, alive and dead. It's just like the tossing of a coin where either you get a head or a tail. So here you get alive or dead, but in principle a quantum particle can take any of the available quantum states, which can actually go from n equal to 0 to infinity. Here we are, for our own convenience, we are giving examples. There are two basis states possible, and we are these basis functions or the basis states that are possible, and the amplitudes are only 2. And why it's 1 by root 2 is very clear, because there is a priori there is a half possibility of that being dead and the half being alive, because there's random possibilities just like coins. And so this is the basic idea of this wave function. The wave function can be expanded in terms of the basis functions, and this is what it means. Okay, so I'll give you an example of this cat or the coin tossing, but they mean the same thing. It's just that if you have infinite number of basis functions, so these basis functions are not 1 or 2 or 3 or 4, this could be actually infinite number of basis functions, then these basis functions, they actually form a set which is called as the Hilbert space. This is the name of a mathematician, and so if it is infinite, then it's called as Hilbert space. If it is finite, just like the cat's example, it is just called as a linear vector space. Okay, and so this is the basic idea of the basis and how the state of a particle or the wave function of a particle is written in terms of the basis states. Okay. All right. So now coming to the operators. Okay. So this is the basis. The wave function, and now we'll talk about operators, because that is what will give the physical observables. So what are the physical observables? The physical observables are the momentum of a particle, okay, which is we know that in non-relativistic mechanics it's mass into the velocity. Energy is an observable. Energy, the total energy of the particle, or just the kinetic energy of the particle, is an observable. There could be other observables, such as angular momentum is an observable, and there could be others as well. There is something called parity. Parity is just a right-left symmetry. So if you stand in front of a mirror, your right hand becomes your left hand and left becomes right. So that's also a property of a quantum system, whether it has a right or left inversion property, and that's called parity. So that's a physical observable as well. So any physical observable is associated with an operator, okay, and this operator is actually a matrix. So operators have matrix representations. All right. So what's a matrix representation? You know matrices. These are we can talk about matrix n cross m, but mostly we talk about square matrices. Say for example n cross n matrix and so on. And these so each of the operators that we have talked about, such as momentum, such as position. Say for example, if the position operator acts on the wave function, it will give you the position of the particle. Okay, and so this has a form which is that of a matrix, and this corresponding to observables, these operators or these matrices are Hermitian matrices. Again, in the name of a mathematician called as a Hermite, and this is the Hermitian matrices are the matrices which gives you real eigenvalues. So because these are observables, they correspond to physical quantities that are measurable in experiments, and because they are measurable in experiments, they must be real quantities, and that's why each of the operators, they need to be Hermitian, and Hermitian operators only give you real eigenvalues. Okay, so let me tell you then what is this operator and eigenvalues that we are talking about. So I've told you that the wave function is a complex quantity which by itself does not have a meaning other than it being a function, a mathematical function. It only acquires the meaning if we take a mod square of that, which becomes a probability density, which when integrated over all space will give you the total probability of finding the particle, which is equal to 1. And now we are talking about operators, and the operators have this property that they are Hermitian, and Hermitian means that they have real eigenvalues. Now I have to justify what I mean by eigenvalues, and what I mean by eigenvalues is the following, that you know so let's have an operator A, could be any operator, and this, when I write it as A, I am not focusing on whether it's a momentum operator or a position operator or an energy operator, any operator, and this usually is written with a cap on top, okay, just like this, and this acting on the side gives me an eigenvalue, okay, this is a German word, and returns me the wave function itself. So an operator acting on a state of a particle gives me a value corresponding to that state and returns me the wave function. Okay, and this is called as the eigenvalue equation. This is called as the eigenstate of A, of this operator A, and this is called as the eigenvalue of the operator A. Okay, so which means that just like you need to measure something, and like you did the measurement on the cat, the state of the cat, or the whether it's being alive or it's being dead, so you need to do a measurement. So there you did a measurement and found that the state of the cat collapses into one of the two available states, which are, let's call them as eigenstates now, because those are the only two states possible for the cat. For a quantum particle, there are many such states that are possible, and when one does a measurement, it corresponds to, or rather it collapses into one of those states. Okay, it is just like the coin is a quantum particle when it's in the air and it's still, you know, spinning. When it goes and lands on the ground or on your palm, it no longer remains a quantum particle because you have made a measurement and you have say you've got a head out of that measurement. So it's just in that similar form. A would be an operator which would make a measurement of some property, whether the cat being dead or alive, or whether you have won the toss and elect to field or elect to bat and things like that. So this is that operator. There are a number of states that are possible because the psi is a linear combination of all the basis states. Okay, and then it goes and gets locked onto one of the specific measurement and the system collapses onto that specific measurement. Okay, so this is what it means by these operators and their physical you know meaning that goes with. So let me also tell you that in that same connection there is a quantity called as the expectation value. So expectation values of operators. And the expectation values of operators is different than the average value of a given observable. Okay, but what it means here, it could be same, but it could be also different. If you take an inner product of this quantity, which itself is a matrix, because A is a matrix which acts on a column vector and gives me a matrix, and I now take an inner product or the conjugate bra of this vector of this wave function here. So this is called as the expectation value. So this, according to that relation that we have written, so we have a so this psi and A psi, okay, where A is the eigenvalue of psi. Now A is just a number, so A can come out from in between, and A can be written as a psi and a psi, and this is the this is exactly what we have written here on the other side, which is equal to 1. That's the normalized, if psi is normalized. If psi is normalized, then that's equal to 1, and we demand the psi to be normalized for that reason, because the probability is normalized, okay, because the total probability is equal to 1. So this is equal to 1, and hence we get the expectation value of this operator A to be A on these state. But there is something more to this. Let me write it in that fashion that we have written it earlier. And so this psi is actually it has a form which is psi equal to sum over n, alpha in some coefficient, some constant, and some phi n, where phi n's are the basis states. This is what we have written. Okay. Now this is an operation that has to be written. So we'll write that as so this psi can now be written as sum over n and some alpha n star, and instead of this ket phi we'll write a bra phi. Okay, so this is that thing here. But when we take this inner product of this pra psi a ket psi, then we'll have to use two different indices, because if you use the same index and multiply two matrices, then you are only considering like terms, that is A1 into B1, A2 into B2, but you need to consider all kinds of terms. So what we'll do here is that we'll use a M here, and we'll use alpha M star, okay, and a phi n m, sorry, phi m, and then a, and then a phi n, and then alpha n. Okay, so that's the thing that we have used, and alphas are, of course, as I said, they are coefficients, so they are like numbers. So there's a summation over m and n. So there's a summation over m and n, and you have an alpha m star alpha n, and we have this equal to a phi m acting on this, and so on and so forth. Okay. So these are the form of these expectation values in terms of when the basis functions are given, and so these are in terms of the basis functions, and this gives you the probability, because you remember that if we have we just take a psi here, and then we have a n and a m, and we have a alpha n star, or we have taken we can write it as m star, and then there is a phi m, and then there is a phi n, and then there is a alpha n. So this is equal to n m alpha n alpha m star and a phi m and a phi n. Now this inner product of phi n and phi m that you see here will have to vanish. Vanish means it's equal to 0 unless n is equal to m. And why is that? Remember that dead and alive, so these are the two deads and this one is alive. A cat cannot be at the same time be dead and alive. So each of the states of the cat should be orthogonal to each other. Orthogonal means that if this is happening, then the other one will not happen, or any of the other ones will not happen. And if something else is happening, excepting that, all the others will not happen. Okay, so which means that this is equal to a delta function which is written as delta nm, and so this is equal to I'll just write it here. So this is equal to a alpha n mod square sum over n, and so on. Okay, so that's the, so I take alpha 1 square plus alpha 2 square plus alpha 3 square all the way there, and that tells me that this which should be equal to 1, because these alphas are, alpha n's are the probabilities of these states occurring. Okay, just like 1 by root 2 we have written it for the cat. Okay, so this is in in simple language that is required. There are more things that are required, of course. You have to prove. Let me give you that as an exercise, that that some of these things you should work out yourself and convince yourself, because there is something quite new for you. So one of the things that are very important to know is that there are, see, the position and momentum are the two very important observables in quantum mechanics, along with energy. Okay, we are not talking about energy now, but energy will come at some point. So this position and momentum, and let me write it by x, and momentum I can write it by p, or in some books you see that it's written as px, but as long as you know that you are in one dimension, px and p would mean the same thing, because there is no py and pz. Okay, so we are just talking about one dimensional particle, but just to make it more concrete, we can write it as x and px. Now, this x and px are two operators, and these two operators are called as non-commuting operators. And what I mean by non-commuting operators, that means that x px is not equal to 0. Okay, so it's important to know that whether you first measure the value of x and then measure the value of px, or you first measure the value of px and then measure the value of x. So this particular thing means this is called as a commutator bracket. If you have been taught earlier on the Poisson bracket in classical mechanics, so this is analogous to that. So this is equal to, the definition is equal to x px minus pxx, and this, by the very uncertainty principle, it should not be commuting, which means that it really these two quantities cannot be measured simultaneously. If two operators commute, which means suppose two operators are a and b, some arbitrary operators, if they commute, that is there, it's equal to 0, which means that ab minus ba is equal to 0, which means AB is equal to BA. So these are operators. Do not think that they are simple numbers that we are talking about, because AB is otherwise always equal to BA. But here they are operators, and they may not commute. In most of the cases they don't, at least the operators that we'll see. But here they don't commute. The commutation relation gives you a value which is IH cross. Okay, we can prove that very easily, and I'll give you. If you take this psi and take this operator, I mean this commutator, and then this becomes psi x px minus px x psi and so on, and this becomes equal to um, x, because x acting on the psi will give you a x, that is the position of the particle, because this psi is a wave function of the particle. So x is an operator now acting on psi, will give me the x, and this will have a so this, and then you have a minus IH cross ddx. So that's the form of this momentum operator, which is in the real space. It looks like minus IH cross ddx. Let me try to give you a little more. Okay, so this is just give me a moment. Try to make it more clear. Yeah, okay. So this is equal to x and px, which is equal to this and a psi, and then it's a minus of minus IH cross ddx, and then a psi x psi. Okay. Once again, let me just take a moment here and say that this is nothing but, so this quantity, I'm writing it here, okay, and that is nothing but a psi star and a minus IH cross ddx, You can call it a del x because usually it's written as del x, but since it's one dimension and we know that the del x and ddx would be same, so this is equal to that. Okay. So now what happens is here, okay, I'll have to shift there itself. All right. So this is equal to minus IH cross and x ddx. Well, minus IH cross is just a number, so it doesn't matter. And a psi which is equal to and there is a plus IH cross, plus because the minus and the minus becomes a plus. So IH cross and a ddx of x psi. Okay. So I can simply open this minus IH cross x ddx of psi. This is equal to plus IH cross psi because I do a chain rule of derivative here. First I take a derivative with respect to x, x with respect to x, so that gives you 1. And then there is a plus IH cross, then I keep that x to be same, and take a derivative of this with respect to psi, and this is that. So the first term and the last term cancel and I get a IH cross psi, which of course should become equal to 1 because these are normalized. So your xpx is equal to IH cross. So which means that the position and the momentum operators do not commute. Okay. So it depends which order you operate them on the wave function to find their respective observables. And this is also related to calculation of, or rather it justifies the Heisenberg's uncertainty relation, which says that that you can there is a delta x delta p is equal to h cross by 2. Okay. And I have also told you how to calculate. Suppose you want to actually calculate the delta x, which is the uncertainty in momentum, and you want to calculate delta p, and these definitions are that it is x square expectation minus x expectation square, and this is also p square expectation minus p expectation square. And now you know how to calculate these expectation values by the prescription that we have given, and we'll of course do more problems in order to clear these concepts, but these are the ones that are you can calculate this x square expectation between the wave function, x expectation, p square and p, and can calculate delta x and delta p for any given problem, and it is guaranteed that delta x and delta p will obey the uncertainty relation, which means for a quantum particle it will be proportional to h cross. I mean, it could be h cross by 2 or h cross by 4, it doesn't matter, but the scale will come as h cross. Okay. I now would do something very important, and it is called as the derive an equation for the wave function that the wave function should obey. Okay. Just like in your Newton's laws, you have written down an equation which is mx double dot equal to F. Okay. So the force is equal to mass into the acceleration, and the solution of which give you x as a function of t, which means that the position of the particle as a function of time lets you know exactly how the particle is propagating from one place to another as the time progresses. So here we do not have x and t explicitly. We cannot talk about the specifying the position and time, but we know how to get information using this. So this should obey an equation just like Newton's law, and this equation is something that we want to find out. And this a priori, this obeys an equation called as a Schrödinger equation. Again, the name of a person, so it's Schrödinger, R, and then there is an umlaut. It's a German thing. So Schrödinger equation, and we'll not derive Schrödinger equation, but we'll say that it is the plausibility argument to derive this equation. Okay, it will take about 10 minutes, so maybe I'll overshoot by a few minutes, but not more than that, probably even lesser than that. Okay, so how do we get a differential equation which satisfies all the properties of the quantum particle that we are aware of? It has inherent, the uncertainty principle, the de Broglie relationship, energy conservation, everything. And what is that equation and how do we get that? So the first thing that it should satisfy is the de Broglie relation and what we call as the Planck's postulate, or you can also call it Einstein's energy relation. So nu is equal to E over H. You have seen all of that, okay, in the photoelectric effect we have used, and this was Planck's idea initially, that the energy of the photons, they are quantized in terms of their frequency as h nu, and there's nothing between E equal to h nu and 2h nu are possible. So there's nothing like 3.5 h nu. I mean 3.5 means 3 by 2. Sorry, what I meant is 1.5. All right. So this is the this Schrödinger equation should be consistent with these two assumptions. It should also be obeying the energy conservation. This is the kinetic energy. P may not be a continuous variable, and P is actually for quantum mechanics it's a an operator which we have seen, P equal to minus IH cross del del x, and V is could be a function of x and t, but in most of the cases, at least for you, it's only a function of x, and most of the time it is also a constant. And the third one, the equation must be linear inside this equation. So all these Schrödinger equations should obey, respect, whatever you want to call it, these things. So it should be linear inside, which means there should not be any term which is like psi into d psi dx or psi mod square or psi square in some form. Okay, it's and if that happens, then of course if it's a second order equation, then there are two solutions, psi 1 and psi 2, and then C1 psi 1 plus a C2 psi 2 will also be a solution of that equation. So these are some of the prerequisites. We make an assumption just for simplicity, that is V of x is independent of position, and let's just call it as V naught. Okay, so that's a constant potential, as if there is a constant potential that hinders the motion of the particle or the position of the particle, etc., and so on. So it tells you that if this is the case, it makes a little simple because the force acting on it is 0. So this tells you that F is equal to minus del V del x or grad V, so to say, and this is equal to 0. And you know what happens when force is equal to 0? The linear momentum is conserved. Okay, and this is what we mean. We mean that your momentum is conserved, which means your lambda is constant. Okay, so not only momentum, because the energy is conserved, So we have both lambda and nu, they are constants. Okay, and so we can think that the solution is sine kx minus omega t. Solution means the wave function should obey sine kx minus omega t or cosine kx minus omega t, where omega is equal to 2 pi nu. Okay, um, sorry, did I write it correctly? It's probably nu equal to omega by 2 pi. So 2 pi nu, fine. Okay. All right, and k is equal to 2 pi over lambda. Well, lambda is the wavelength. Okay, so this wave function should obey these two property. Now, if we put all of them together, then your h cross square k square over 2m, that's the kinetic energy, because P is equal to h cross k, plus V naught, that's purely from the energy conservation, should become equal to h cross omega, or which is equal to h nu. So this is equal to h over 2 pi and omega. So omega by 2 pi is equal to nu. So that is fine. Okay. So this is the energy conservation. So if the energy conservation is like this, now you see, how do you get a k square from here? You have to take a second derivative, because the k will come out from a space derivative, second derivative with respect to space x. So, and how do you get a omega? Omega you will find by taking a first derivative with respect to time. Okay. So this equation, Schrodinger equation, so to say, obeys a relation, or that equation connects the second order space derivative to a first order time derivative. And this is little strange, because we have learned in your relativity course that this is not Lorentz invariant, and this is not Lorentz invariant indeed, and that's why it is not the most correct thing. So it's only valid for non-relativistic cases. So what we do is that with that presumption, we write it's d2 psi dx 2 plus a v0 psi xt, which is equal to beta d psi xt dt. This is exactly what I said earlier, that whatever equation that psi will have to follow this, which is a second derivative with respect to space, is connected to a single derivative with respect to time, and then there is a v0 there. Now, the only thing that needs to be determined is this alpha and beta, and once you do that, then you have then you can get this equation. Now, if you take one of these, say sine, if you take sine, then I'm not writing down everything, but what is second derivative with respect to space would give me a sine kx minus omega t with, of course, k square. This is sine again, but d psi dt will become cos. Please put in all these other things. I am not put in. This one gave me sine, this one gave me sine, and this one gave me cos, because I take a derivative with respect to t. Now, this is very difficult equation to satisfy, because cos and sine are out of phase by pi by 2. Okay, so this will be a very difficult thing to satisfy. So a simple solution of this is that what you do is you take a solution psi of xt, it's equal to, say, cos kx minus omega t plus some coefficient, again doesn't matter, it's some gamma sine kx minus omega t. Okay, So this is a smart move, because since each one of them is not going to satisfy your equation, but a combination of that, you don't mind that to be a solution, and where gamma is a constant. So if you put it in the above equation, you get a minus alpha k square plus a v naught plus a beta omega gamma cosine omega kx minus omega t plus alpha k square gamma plus a v naught gamma minus beta omega sine kx minus omega t. This is equal to 0. And of course, if you see this equation, it cannot have that cosine and sine equal to 0. So which means that if this the right hand side is equal to 0, then the coefficient should vanish. Okay, and the coefficients vanishing will give me two equations, which is minus alpha k square plus a v naught, which is equal to minus beta gamma omega, and minus alpha k square plus v naught equal to beta omega gamma. And you can call it as equation 2 and 3, and the original equation, that is equation 1, which is this one, to be equation 1. Okay, so if you solve 1, 2 and 3 simultaneously, what you get is that gamma equal to plus minus root over minus 1, which is equal to plus minus I, and so on. And if you put this into this equation, say in 2, so putting it in 2 will give you a minus alpha k square plus a v naught, which is equal to minus plus I beta omega. If you compare this with alpha h cross square k square over 2m plus a v naught, this is equal to h cross omega, that immediately tells you that your alpha is equal to minus h square by 2m and beta equal to plus minus I h cross. Okay, so I go back to the original equation, and let me write that down here. So this is equal to minus h cross square by 2m d square dx square psi xt plus v naught psi xt is equal to e psi xt. Okay, this is called as the Schrödinger equation, and this equation, when you solve it, you get psi, and when you get psi, you get a lot of other things that we have talked about earlier. And our next aim would be to take this psi, or rather calculate this psi for a variety of v. We will not put that v to be constant always, but we'll put that to be, in general, it's a function of x and t. None of these other things, they are violated. It's only that we had a simplification in understanding that there's no force, so momentum is conserved, etc. Energy will anyway be conserved in the process, and there'll be no problem otherwise. And so this equation will give us a psi, and this psi will have to be solved for some potential problems, which is our next task.